In this second video on the polycyclic aromatic hydrocarbons, that is PAH, we are going to see the second important PAH, that is anthracene. We are going to see its structure, its nomenclature, its reactivity, various resonance forms, and its various reactions, its synthesis, its applications, as well as its derivatives and their uses. Let us see first. Anthracene is a linear tribenzene compound. 3 benzene rings are fused orthogonally to each other with a molecular formula of C14H10. Its numbering is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Anyways, 9, 10 are going to be same. It is a tricyclic compound, so tricyclo, and tetradeca, that is you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So tetradeca 14, heptane, and heptaene it is actually. That means indicating that it has got hepta, means 7 double bonds, 1, 2, 3, 4, 5, 6, 7. It's a black colored crystalline compound, dark black colored. On standing it becomes darker and darker. Its molecular weight is 178. In pure form it is colorless. It has got a weak typical aromatic odor. It's having a higher melting point than naphthalene, quite higher, almost 3 times. Anthracene, benzene rings are linearly fused and it offers 4 resonance forms. These are 4 different resonance forms with alternating double bonds, and therefore it is resonance stabilized. It's obtained from the anthracene oil of the coal tar fraction. As we saw, anthracene oil is the higher boiling oil from the coal tar, which distills from 300 to 350 degrees centigrade. After distillation, this is purified by sublimation. Coal tar plus, when it is distilled, anthracene oil fraction comes. It is cooled and pressed, so you get a solid dark colored anthracene cake with a phenolic compound called carbazole. Plus you also get some phenanthrene anthracene mixed with it. Now this is powdered and is treated with solvent naphtha, that is again a hydrocarbon solvent. So selectively phenanthrene is removed. This is then carbazole is washed with a basic solvent like pyridine. So carbazole is totally dissolved in pyridine. So what you get is actually the anthracene. This is heated and sublimed, and you get solid. It's directly converted into gas. What is sublimation? Sublimation is like a vaporization of a solid, and it doesn't condense into liquid, but it directly becomes solid. Two examples are iodine and sulfur. You can try in an experiment. Actually, you can take a beaker, a few crystals of iodine, and you can cover the beaker's mouth with a watch glass or a petri dish and heat it on a heating mantle or a hot plate. Slowly the beaker will be filled with iodine vapors. All the iodine crystals will melt and they will vaporize. And when you remove this beaker immediately, after all iodine is vaporized, keep it at room temperature on an asbestos sheet. Slowly the walls of the beaker will have, the crystals will deposit, which are quite pure. So this is sublimation. Same thing happens with sulfur also. So anthracene is sublimed and purified to a purer melting point of 216 degrees centigrade. So initially with carbazole you get a brown colored solid. After washing with pyridine you get anthracene, and after sublimation you get quite crystalline granular compound. So the question can be asked how anthracene is commercially obtained. So you have to explain from coal tar to final, all these steps. Fine. Now we will talk about its isomerism and nomenclature. It has four canonical forms as I've shown. So these are the resonance forms, and you can start numbering it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these two positions, like naphthalene, are called alpha. And these two positions, these four positions 1, 4, 8, 5, 5, 8 are alpha, and 2, 3, 6, 7 are beta. Because they vary in their electron density and of course their reaction towards the electrophile. This readily react, this takes little more time. So question can be asked, explain the positions of double bonds and numbering in anthracene. So you have to give these four forms and the numbering. Fine. Let us go to the synthesis of anthracene, and you have the same Howard synthesis. I told you this is going to come for all the three derivatives, only the reactants will change. There also it was benzene, here also it is benzene, only the anhydride has changed. There it was a succinic anhydride because we wanted to add only one more ring, and so 2 carbon units was there, and then we formed bonds. So we could add more to that. But here we have one more benzene ring, so we use phthalic anhydride. So with aluminum chloride, there is a classical Friedel-Crafts acylation to get orthobenzoyl benzoic acid. This is benzoic acid, and orthobenzoyl benzoic acid. This is benzoyl group. This is dehydrated with H2SO4. So one H from here and OH. So you get a dione, which is called as 19 anthraquinone. And this same like in anthracene, you distill it with at high temperature. This anthraquinone is molten and distilled off with zinc dust. You get anthracene. So this is ready. This oxygen is removed, and you get a zinc reduction type of thing. So the first step is benzoyl benzoic acid formation via Friedel-Crafts acylation by the reaction of benzene and phthalic anhydride in the presence of aluminum chloride. Second step is dehydration with concentrated H2SO4. So it's dehydrative ring closure. And last is Clemenson type of reduction, forming CH2 group or CH groups. So you get anthracene. There is a second type of synthesis, Elb's reaction, where you get the orthomethyl benzophenone, and this at a very high temperature at 450 degrees centigrade. It loses water from here and here, and it cyclizes to anthracene. So polynuclear hydrocarbon is prepared by pyrolysis of a diaryl ketone. This is called as Elb's reaction. The orthomethyl benzophenone, upon heating at a very high temperature, loses a water molecule and forms anthracene. Next is of course this third synthesis of anthracene, that is a Friedel-Crafts reaction, where you actually interact. It's an intramolecular Friedel-Crafts between the two molecules, intermolecular Friedel-Crafts between two same molecules like benzyl chloride. So there are two Friedel-Crafts taking place. One is here and another is here. And finally, the loss of 4 HCl molecules. This happens at room temperature in carbon disulfide with AlCl3. And then this is further oxidized to get anthracene. There is another type of Friedel-Crafts reaction, like you just start with 2 benzenes and 2 molecules of methylene dibromide with AlCl3. So two carbon units are added here. So you get a 9,10 dihydroanthracene, same thing, and again you oxidize it, so you get the same compound. So these are the 4 different methods of synthesis of anthracene. Now let us see the orientation of substitution. Anthracene actually is more reactive in the inner ring A here as compared to the outer ring B. In the form B is the outer ring, this alpha position or beta position, but it is in the inner ring, that is the 9 position. And this we can understand by looking at the structure that the A contributor has one resonance contributor in which the positive charge is within the ring. It doesn't spill to the outside rings and it doesn't destroy their benzenoid structures. However, if you take this outside, then this stability is damaged, and therefore this contributor is not possible there. So cation A is of lowest energy and is more predominant, and this happens only when the substitution occurs at the central ring. So in case of anthracene, it is a central ring which is rather a better source of electrons and which preserves gives you a benzenoid intermediate of less energy and more stability. So either it gives you here or it gives you here. So it gives you several canonical forms, but you can get this and these 2 canonical forms which you got is only possible if the substitution is at the central ring. So it is more preferred. Even you will see that the electron density map, this is more stable, 9 position, theoretical and calculated, and the actual found estimated are lower compared to the alpha and beta positions. So the 9 position has lower energy than the positions 1 and 2. Now let us go further to see various chemical reactions of anthracene. And like naphthalene, it also undergoes oxidation under mild conditions with dichromate oxidation, that is chromic acid, sodium dichromate with H2SO4 will form chromic acid, and that chromic acid oxidation gives you the mildest form, that is the dione, anthraquinone. And of course this is not taken further to ring breaking. If you try to break, it may give you the orthobenzoyl benzoic acid like this, or this may give you orthobenzoyl benzoic acid. Reduction is with a simple sodium Hg in alcohol. You just get the inner ring is reduced. If you go further with a noble metal like Rani nickel and hydrogenation, power shaker at high temperature, both outside rings are reduced. You get an octahedro. This is a dihedro. This is octahedro. If you take it further, the entire system is reduced and you get completely reduced product. It can be reduced in presence of zinc amalgam to form 9,10 dihydroanthracene. If reduced in presence of Rani nickel, it gives you octahedro, which can be further reduced to a fully saturated form. Then comes the halogenation. Like naphthalene also, if you, in this case, you go for halogenation and chlorination in carbon disulfide or passing or just sulfuryl chloride, you get first dichloro, 9,10 dichloro, which collapses to 9-chloro, which is more predominant. However, if you use 2 moles of chlorine and reflux it in carbon tetrachloride, which is higher boiling than the carbon disulfide, you may land up with a mixture of the 9-chloro and 9,10 dichloro derivatives. Nitration also similarly, it under mild conditions will give you only 9-nitro, but if you proceed further, it will give you 9-nitro plus 9 and 9,10 dinitro mixture. Anthracene with on sulfonation will first go to under mild conditions will go at the ninth position, but if you force it more, can also give an additional byproduct of beta sulfonic acid. While with excess of the reagent like concentrate H2SO4, you may get a product mixture where it goes to 1 and 8 anthracene and also 2 and 7 anthracene. So you get a di-alpha and di-beta anthracene sulfonic acids. The classical formulation with Wilsmer-Hack reagent. Wilsmer-Hack reagent is POCl3 and DMF or methylphenylformamide. Generally, it is done under ice cold conditions. Wilsmer-Hack can also be done with POCl3 and a catalytic amount or equivalent amount of dimethylformamide, but the reaction can be done in carbon tetrachloride or toluene also, and that is at a higher temperature. But this is at a classical this thing, and it will selectively go at the 9th position, and the byproduct is of course the N-methylaniline. Diel-Salter reaction is when anthracene is reacted with a dienophile. Anthracene itself is a diene actually. It has got a diene in the center. So diene, conjugated double bond system. And this is another double bond containing a system which is a dienophile, which has got a very good affinity for this diene system. So it forms these both places, they form a adduct with this diene. And when heated with malic anhydride is one of such dienophile, it forms an adduct 910 anthracene malic anhydride. On similar this thing, if it is if you take it with a dienophile like this triple substituted benzene derivative, it forms a adduct. So such rings are called as endosystems, bridgehead systems. Anthracene is even more reactive than phenanthrene and has a greater tendency to add at the 9-10 positions than to substitute. However, the addition products of nitration and halogenation readily undergo elimination to form finally the 9 substitution product, which is more stable. A few derivatives of anthracene is one is alizarin, which is prepared from anthraquinone sulfonic acid. And when this is treated with NaOH and you can say sodium chloride, it undergoes oxidation and it gives you a diphenol type of compound, which is alizarin, and it's used to be a dye of a splendid red color. It was also used in pharma products. Nowadays, not much used. It's replaced with amaranth, which is from natural source. Anthraquinone, aminoanthraquinone to aminoanthraquinone is basically a simple nucleophilic substitution of the sodium sulfonate of sulfonic acid, sodium salt of anthraquinone with ammonia. You get the 2-aminoanthraquinone with sodium hydrogen sulfate, and this 2-aminoanthraquinone is an intermediate for indanthrene types of dyes. Other derivatives of anthracene is 1,2-hydroxy and anthracenes, that is called as Anthronols. Starting with the anthracene 1 sulfonic acid sodium salt with NaOH, you cook it, so you get a rearrangement, and this shifts to the second position. You get a phenolic OH here, sodium salt, and when it's hydrolyzed, you get anthronols. And instead of that, if you started with 2-hydroxy, you will get 2 anthronols. Fine. These are both brownish solids. Yellow, one is a yellow solid and one is another is a brownish solid. 9-hydroxy anthracene is also called as anthronol. That will be called as 9-anthronol. So it starts with a 9,10 anthraquinone, which is reduced at the 10 position with stannous HCl glacial acetic acid, and then which is heated, it quickly tautomerizes to what is say anthronol, 9-anthronol. 9,10 dihydroxyanthraquinol is simply the 9,10 anthraquinone is mildly reduced with zinc dust in alkaline conditions to give you anthraquinol or 9,10 diol. We also have the anthroic acids, 1,2 anthroic acids. So these are again from the sulfonic acids. 1,2 sulfonic acids are converted to their sodium salts, and then they are fused with sodium cyanide to get the corresponding cyanoderivatives. And these are hydrolyzed with a acidic or basic pH. So the CN gets converted to CONH2, and then after further hydrolytic attack, it becomes COOH, and the NH2 is knocked off from the amide. So it's go as the amides. In all nitriles get hydrolyzed to COOH is through their intermediate amides. The first molecule of water gets added across the C triple bond end to form CONH2, and then that NH2 is knocked by further OH nucleophile to give you COOH. 9-anthroic acid is also obtained via anthronoil 9-carbonyl chloride. So this is just with oxalyl chloride basically. This is COCl, oxalyl chloride. When it is treated, it gives you COCl, that is an anthracene 9-acid chloride, which is hydrolyzed to 9-anthronic acid and is structurally related to certain alkaloids like morphine, steroids like cholesterol. And anthracene, actually the oil fraction comes from coal tar. And next is of course applications of anthracene. Anthracene is used for making dyes like alizarin, which we saw, used for manufacturing anthraquinone, parent substance of large class of dyes and pigments. Anthraquinone is a rich source for large number of dyes and pigments. It is also used in wood preservatives, insecticides, and coating materials. It is used as a scintillator for detectors of high energy photons and electrons, used as an organic semiconductor. And the hydroxyanthracene derivatives like anthracene and anthracenol are pharmacologically active. And yes, again, it is used as a scintillator of detectors of high energy photons for alpha particles. So dear friends, this is the second video where we have discussed anthracene completely. The third video we will see the third derivative, and that is phenanthrene. So I hope this video was useful to you, and I expect you